Well, I'm really excited to get to wrap up the conference because I think a lot of the ways that the work that we do is really trying to bridge across a lot of these conversations that we've had over the week. And the other cool thing about the work that I'm going to present is it really features many of the people in this room. Our research team in particular, some of which is already back in our lab doing some testing. But also the families here. We couldn't do any of this without you. And so I'm really appreciative to you and to Leah for helping us kind of connect, and really to all the other scientists too, to kind of starting to learn from each other. So I am currently in the Bernier lab for another week. And so this is my last Bernier lab talk. So I'll try to be as energetic as Rafe, if anyone could do that. And I'm going to talk specifically about the human brain biomarkers that we see. And thank you very much to the Family's SCN2A Foundation for my very first grant as an independent investigator. I'm really excited and I hope to make you really proud. And I'll present some of the preliminary work here today. So you've seen the overviews, I hope, in our pamphlets, but I'm really hoping to sell you on why it's really important that we look at these human biomarkers or brain markers. And I want to spend a little bit of time of actually showing you what that looks like. Because I think sometimes it's hard to know what that means in our laboratory settings. Many of you parents have sat through and could probably do as good a job as I as explaining it. And then I'll share a little bit of our preliminary findings. So I also wanted to bring us back to the central mission of Family's SCN2A Foundation, right? So we're all here to really think about how we can use therapies, whether they are pharmacological or whether they are play-based or PT, OT, working with all kinds of clinicians. And ultimately, our goal is to really improve our children's lives, right? So we're working towards that cure, but even incremental progress towards improving each child's life is really what we're looking to do. And so one of the ways to do that is to really assess how well these therapies are doing. And it's a really tricky problem. As you have heard from Dr. Gertz yesterday, all of our kids sometimes have trouble telling us what they're able to take in the world and how they are kind of perceiving information and what that looks like to them. And so how can we actually use some of our technology to kind of give them a voice and share at a quantitative level how well some of these therapies are doing? So I like to think about this, all of these pieces are part of the phenotype, right? So we know that these children have a mutation to SCN2A, but ultimately all of these children might share some commonalities across all of these different levels, right? So if we work up this little pyramid, we're going to see some of these variants are going to share common problems to some of the circuitry, and we've spent a lot of time talking about a lot of these kind of bottom rungs here, which I'm really excited to learn about, and I've been furiously taking notes. And really what happens is when we get to the top and we're looking at these diagnoses, the children look a lot different, right? So how can we actually connect across all of these different levels to truly inform how we can move forward with treatment for each child? So this is very much like that precision medicine kind of idea that we talked about this morning. So if we think about kind of these macro levels, we see autism, we see intellectual disability, and we see other children that have early seizure activity. And we spent a lot of time this conference talking about how these relate to those kind of functional variant roles, right? And what's common for both loss of function and gain of function variants is that they share this intellectual disability. But what we see is unique are these autism, these different profiles, right? So hopefully everyone's kind of come around to this idea. So what the goal of our work is to look somewhere in the middle here. So we have the top level, we have the bottom level. Well, what's going on kind of in basic sensory processing, information processing? So we're constantly our brain is just taking in information every millisecond of the day. How are these children really taking in that information? And that's what I'll hopefully address today. So for anyone who hasn't had a chance to see our style of EEG, it looks very different than what you might see at the hospital while you're doing a seizure panel or a sleep study. So one of the great things about our technology is that it's incredibly safe and painless, non-invasive. And if you could play the movie. This is a baby for my graduate work, and I wanted to showcase how easily the net goes on. So there's no glue, there's no gel. This baby is just kind of chill, and then you pop it on, and we usually have a RA helping out with some really fun things to look at. And then within a couple of seconds, now you're able to start recording EEG. So hopefully I've already convinced you from this alone that that's a huge advantage here. And one of the great things is that then we can use this technology to look at those passive brain processes that are just implicit, that even if the child can't give us a behavioral response, as in pre-verbal infants or our nonverbal children, we can still look at kind of at the millisecond level how their brain is taking in this information. And what's really, really cool is that when you take this long string of EEG information, you can chunk it up and say, all right, well, how is the brain processing this face or a sound? And we can actually look within the first half a second and look at different stages of cognitive processing. So we can look at early detection of that information, and we can look at how the brain is actually taking those early detected whatever it's seen or heard, and then making some extrapolation about what that actually means, right? So there's a lot of different stages that go along, and with EEG, we can do that very, very rapidly. And then the other thing that I am super fired up about is we can actually look at implicit learning patterns, right? So we can look at how these responses change over time, and hopefully I'll convince you by the end that that's really important for our kids in particular. So what are we measuring? We spent a lot of time talking about cellular level, and I hate to say it, we can't look at that with EEG, right? So we're not looking at one single cell's response, we're looking at a lot of cells' response. So ultimately what happens is when a part of the brain, and here I've just kind of have a little schematic, part of the brain has some activation, and so all of these neurons in this section are saying, hey, there's something important, I need to think about it. And what happens is, just like a single cell does, we see a change in the electricity. And if you could play the video. So what happens is this action potential that is summed from all of those cells has both a negative and a positive response. And we're able to pick up on that. So we pick up on both of those pieces, and when we put on a net on the child, we're able to look at those responses across all of these different channels. So part of the reason why we use these really high density systems is that we can look at the patterns of activation kind of down here at the bottom, as well as up here on the top, because they all mean something, because we're taking these action potential summations from all around the brain, and we really want to target what's important to that cognitive process. Okay, so here's an example of what it looks like. And this is actually recorded at the hotel yesterday. And thank you so much for letting me do a little screenshot and show you what it looks like in real time. So you can play the video. So what you see here are all of these different rows are one of those channels. And what's happening at the very top is you're seeing flags being thrown. So we're basically we're looking at this ongoing EEG. And those sounds you hear lightly in the background. We're trying to figure out how the brain is responding to each of those sounds. And do you see how chill our little guy is doing? I actually wanted to get a little bit more wiggles and movements, but this is amazing brain data. This is just so cool to see. And so we're really, really thankful for all of the heroics that went into this session. Now, it's not always that easy, and hopefully, I don't know if Leah's still here, but if we go to the next slide, I wanted to show you sometimes it doesn't always go as planned, and one of the things that we really try hard is to train all of our team to be able to be flexible and responsive. And so I wanted to show you a little bit of a session where we got exceptional data, but I wanted to show you some of the different strategies that went into this. So if we play this video. So we started out in the stroller, which is nice and contained, and we have just similar sounds you hear, starting to get a little fussy. We don't want the iPad anymore, we're kicking it, no longer interested in anything, we're trying to redirect attention. So then we switch, and we try different ways of soothing. And ultimately, despite all of these behaviors, and these are just little tiny snippets, we got exceptional data. So I know, and I know some of you parents in here in particular in the past couple of days even have shown us heroics, including bear hugs and just working and letting us know when your child's hit your threshold. But even 5 minutes or 10 minutes of data give us really, really bountiful information. So great. So why do we use this as a candidate EEG? Why is EEG a great candidate biomarker? And the answer is really ultimately in all the other talks that preceded what I'm about to kind of go into, because SCN2A is expressed in the brain, right? So, and we see these different kinds of changes to how neurons are functioning at different developmental stages. And one of the great things that Dr. Spiro mentioned is that we can actually measure this continuously, right? So the EEG signature during infancy is going to be very, very remarkably similar to an adult pattern. So we can have children come back and do multiple tests in order to kind of look at how these developmental trajectories are changing, which is fantastic for us. And it's truly accessible, right? So we have lots of children who are not able to sit by themselves, but it's fine to have them in your lap or in lots of different kinds of settings. They can lay down. We can work and accommodate children of different needs. And then lastly, I love this ability to be able to actually look at how these children are taking in information in real time. And granted, it takes us a little bit of effort on the back end to actually make sense of it all, but we are capturing that moment-to-moment learning that's going on. So why study attention? And that's the candidate biomarker that I want to talk about today. So attention is a really, really core, basic sensory process. And there's a really interesting network of brain regions that are responsible for taking in information and processing it. So ultimately, you use your attention system to kind of change and shift focus and choose what to look at. So for example, if we were wanting to orient to a new stimulus, you might look at this picture and maybe it takes you a little bit of time, but hopefully eventually you see that one of those things is not a stuffed animal, but is actually a little puppy. And yeah, so once I show you this first time, I bet you if I show you some other pictures, you might more quickly be able to pick out the pop out, what's not actually what its others are. And so ultimately, it's really important to know when something in the world is different. So our brain, when things are repeated and coming over and over again, our brain responses start to decrease over time, as we saw with some habituation data earlier in the mouse. And then when you see something new, you have a bigger brain response. So ultimately, what we're really interested in is how, when you kind of have this repeated information happening over and over again, what do we see when that new information comes? And how big is that difference within one person? So this is stemming from work that we did with other children with autism, who some had genetic mutations and some did not. But ultimately, what we found in this study is, let me start here and just walk you through kind of what we're looking at. So remember how I said we're capturing kind of the positivity and that negativity? Ultimately, that's what's plotted here. And it doesn't necessarily matter whether it's positive or negative. We're really looking for how big it is in this case. And what we see here in autism is a much, much bigger response to these new things in the world. And what we can do is, these are each individual children. So we can look and say, all right, so each time they saw something different, this new response, how big was that response? And you see a couple control children here, and I have a couple autism cases here. And ultimately, what we found is that in autism, we have a heightened novelty response. So unlike typical development, which kind of habituates very rapidly, so you see this really sharp cutoff down here. This is over trial, so over time, it just decreases very rapidly. Whereas in autism, it stays as a more important thing for longer. So we have this prolonged heightened response in autism. So we are able to build from our previous work. So we have Rafe and our team have worked on the tiger study, which many of you participated in because of your SCN2A mutation. But we also have children who participated in other studies that did the same tasks that either did not have a genetic mutation or were typically developing or had a genetic mutation that is not SCN2A. So now we're really able to kind of look at these different responses and find common biomarkers within children of a certain genetic group that might relate and be different and unique from typical development as well as autism more broadly. So what I'm doing with the Action Potential Grant is I'm trying to supplement our Tiger data set and get as many kids with SCN2A as possible to be able to start to address these questions, because ultimately it's a numbers game. We want to see as many kids and look to see what those common patterns are. So I think Jen talked about this. I missed the very beginning of her talk, but we have children come in and they do a full comprehensive battery. So we're looking at behaviors, clinical presentations, and then what I'll talk about here today is our EEG pipeline. So, and unlike what we've been talking about a lot, and I think this conversation has come up a little bit, we're not able, with all of these new variants, we don't know for a fact whether or not each variant is a loss of function or a gain of function. So we're going to do a little bit of hand waving for our data for now as we continue to work at the molecular and cellular level, where we're going to kind of approximate what we think might be the predominant phenotype. So if children have seizure activities, and we're studying this around that first year of life, as we've talked about, then we're talking about that as being kind of an autism or IDD phenotype with early seizures or without. And so my goal is to get an even number of kids who haven't, who can do the study, who either have fit one of these phenotypes. And I'm proud to say that already, even though this is very early on, we've collected about half of, or have enrolled about half of the numbers of families that we want to be seeing. And so next steps after I leave the lab is to go on a bunch of road trips. So if there are any parents in the room who weren't able to do the study here, or if you know families that weren't able to make it out, I'm happy to come to you. I bring the equipment and we have a good time. So feel free to spread the word. So just to kind of give you a sense of some of the preliminary data, this is a subset of kiddos that were collected before this conference. And we have, I just wanted to highlight a couple of things. So there's 15 kids currently in this data set. And I wanted to just show you what their data looks like related to children who have autism and a different genetic mutation, as well as children who have typical development, to kind of put things in context. And so we have kids that are around between 4 to 11 kind of in this sample. And we have, most of our children have what we might think of as the ASDDD phenotype, and we only have 4 in this data set that have that IEE phenotype. And then the other thing to note here is that I'm matching our other mutation group based upon cognition and adaptive skills, because we want to look at how these brain phenotypes are unique to SCN2A and that aren't necessarily related to their cognitive abilities. So here's I'm going to kind of walk through this very quickly. There's a lot of complicated ways that you can take this data, but ultimately I want to talk about 2 different pieces of EEG data. And these refer to 2 different cognitive stages. So our N1 is going to tell us a lot about low level, this early detection difference, which you can see here, and it's recorded at the very tip top of the head. We record the P3A from the same spot, and this is more related to kind of attention orienting, right? So these are 2 cognitive distinct stages. One is that early, like, oh, something's different, and the other one is, why is it different? What does that mean, right? If you could play the little video at the top. So this is a version of our task. Kids get to watch a video and hear sounds. How many of you have heard Pingo way too many times? So, and this is, yeah, when you're watching it for 20 minutes, it's less exciting over and over and over again. So this is a task that we borrowed from the European consortium that's looking at autism, but we also have our own similar battery. So the concept is we give the kids anything that they want to watch, really. We like it when they watch the video, but anything that'll keep them chill and still. And then we play these noises on top of that. And we're ultimately looking at that auditory response. The other thing to note is that kids are welcome to fall asleep during this task. We did a lot of work on this preliminary data to look to see how the brain response changes when you fall asleep. We even had some parents who did the test fall asleep. And I'm happy to report that it's a really, really robust marker. So regardless of whether or not you're visually attending or really paying attention to what's going on, your brain is implicitly grabbing this information. So what did we find? So first of all, I just want to orient you to kind of how I'll present some of these graphs. This is our typical development group. And I'm highlighting the kind of deviant sound in the kind of purplish color here. And what you can see in typical development is that there's a bigger response to when something's different, which is what we'd expect. And in both of our gene groups, SCN2A and this other mutation group, we saw no condition difference. But what I really, really want to highlight, and actually I think there's probably some stats if you want to look at them, what I really want to highlight is how much bigger these responses are compared to typical development. So they're not necessarily, their brains aren't responding differentially to these new sounds, but it's an overall bigger response, which is important. So when we look at the P3A, which is that component that's more related to ascribing meaning from these sounds, we see that all of the groups are showing condition differences. So we see that the two bar graphs are different, and the brains are more responsive to that new weird sound. But what's really important to look at and hard to kind of navigate through is that in SCN2A, that difference between the new thing and then the repeated thing is much smaller than in typical development. And it's much smaller than what we see in autism and other genetic mutations. So my favorite part is, well, how is this changing dynamically over time? So how is this information coming in and being kind of integrated live in real time? So we can plot these two data points over the course of the experiment. And what you see here in typical development is similar to what I showed before, where you have differentiation, and you have this is for the P3A, and it's across the entire course of the experiment. You see a bigger brain response to this new thing. When we look at our mutation group, it's somewhat similar, but we start to see a steady decline in that frequent response. So this is that repeated sound. It starts out pretty big too, and then also starts to decrease. So what do we see in SCN2A? Well, we see something very different. So actually, if you look at the black lines, the mutation groups look very similar, right? So our other mutation group and the SCN2A group start high, and then that signal is deteriorating. However, it's that response to that novelty sound, it doesn't go away. They're hyper responsive at the brain to this novelty sound, which is very much aligned with this kind of hypersensitivity that we just were talking about. So lastly, and this was very preliminary data because we have so few kids, but I wanted to look at what these patterns look like based upon the variant type. And so when we do that, we actually don't see any differences in that early detection response. So here I'm going to just look at the P3A response. This is that integrating and chewing through the information part. And what we see is that both of the groups are showing that pattern where they are responding differentially to those weird different sounds, but it's when we look at those habituation patterns. So this, I hope you can see how different they are. When you plot them out like this, it's quite compelling. And what's happening is we actually see a very similar response in the ASD-DD group as we do in autism. So we see this kind of prolonged response to it, and that's what we saw on the group level. But when we look at those IEE kids, we see something very different. And I'm going to call this sensitization, which is a funny way of basically saying that as new information is coming in, it's kind of like the brain needs to ramp up. So there's a period where this information is growing more and more and more important, and the brain's starting to pay attention to it more. And so once it reaches a point, then it kind of peters out again. So very different patterns. And this could be really helpful as we start to think about therapeutics, as well as how we actually track progress, right? So as we're doing treatment therapies, how is this actually working? But the biggest challenge for us, and what I'm really excited to talk more with some of the other scientists in the room and families too about what you're seeing in your children, is here I'm really using this kind of basic classification, right? So we kind of hand waved and said, these are how we're dividing our subjects to kind of really start to look at those specific events. But ultimately, what we need to do is work together to kind of look across and understand how each variant actually relates to this gain of function, loss of function profile, and understand if our EEG markers are actually mapping onto that. And I think, so we're hoping to keep working on that piece. The other piece that is different with my grant is that now we're extending the age downwards as well. So we are looking at children of all ages. And so as you saw, we have one baby already who's done stellar, and we're going to see some more kids that are, between 2 and 4, which is not traditionally what we would see in the tiger study. So we're really able to start navigating and looking specifically if there are developmental changes, which I think really maps on well to thinking about how SCN2A is expressed differentially across development. And then lastly, we also do a lot of work with resting EEG, and we also heard some more about how the resting EEG in the mice. And so I'd be really interested to talk some more about what these different profiles look like. But what we look for in the humans is how is the brain organized more broadly, generally. So are there certain patterns? Are the two hemispheres of the brain talking to each other? Is there kind of a certain oscillatory behavior? So are all those ups and downs kind of falling into place in a certain way? And I think that we are on track there to kind of make some steady gains. So I think, yep, so to just kind of wrap it up, Jen Gertz talked a little bit more about some of our behaviors that we're seeing. But we are seeing these really unique, distinct patterns for our two different kind of phenotype groups. And ultimately, the next step is to really pair it together and look at how behavior is translating to the brain, and then how those two responses relate back to the genetic variant, the specific genetic variant. All right, I really want to thank people. So clearly there's a giant team of people that have done this work. We've been fortunate to work with Geisinger and Roche Pharmaceutical to get our first large sample of children with SCN2A. I want to thank all the parents for coming to visit with us or letting us come to you. And I wanted to also put my contact information up. So I, starting next week, will be moving to the University of Alabama. I accepted a faculty position. So if anyone wants to kind of stay in touch with me, I'm hoping to do a lot of longitudinal testing, depending on how the funding goes over the next couple of years. And if you know other people that haven't participated in Tiger or would be interested in doing this kind of home visit with EEG as the focus, please let them know about me. So thank you.
All right.